סגור, בהצלחה.
תודה.
Hey everyone, so for this specific one, I'm really excited because I know Benny for a few years from CYMOTIVE, so I know it will be really interesting. So Benny Meisels is a security architect with over 9 years of security risk experience, in both IT and embedded systems, and now he's going to talk about 90% complete, don't turn off your car, automotive OTA over-the-air update security for connected vehicle. Of course, during the session, don't forget to ask your questions in the question and answer tab, and we will Benny will answer anything he would can at the end of the presentation. And of course, you can raise your hand and come up the stage. Thank you, Benny. It's your stage.
So hello everyone, and welcome to my presentation on automotive over-the-air update security for the connected vehicle. So Eden already gave some of the introduction, so we'll skip what was already said. But besides my work in embedded security, I enjoy working on electronic conference badges, and you can see two of them in the slides. This is actually what got me into embedded security. Previously, I was doing IT security. The motivation for the talk today is that over-the-air updates adoption is on the rise. We're seeing these being deployed in both conventional vehicles, but we're also seeing that they will be really important for the future software-defined vehicles, where functions are going to be updated maybe on a daily basis, and also for commercial autonomous vehicles such as robotaxis or autonomous trucks, which are now slowly being deployed in different places in the world. These fleets need to be updated on a regular basis, and automotive OTA will be a key role in this enablement of these features and these autonomous use cases. Over-the-air updates are much more complex for automotive than for mobile devices, which we're already used to getting on a regular basis. And we'll get a bit in depth in the slides themselves, but just as an opening point, there's multiple ECUs that need to be flashed. It's not a single device, but rather a network of devices. There's different software interdependencies between these different ECUs. You have variants, maybe regional variants or trims for the different trims of the vehicle. You also have some legacy ECUs, which must be using older connectivity, and we need to also update those. So we might have to find a way to have an adapter between a newer system and an older system in the vehicle. Additionally, the cost and the implications of a failure for software update in automotive can be catastrophic. First of all, it can be safety issues. If the update code, especially the early code, download code, it can cause some problems. And additionally, brand reputation can be hurt by this if the software update doesn't work correctly. Additionally, at CYMOTIVE, we believe that the regulations, which we'll speak about shortly as part of the presentation, are minimum requirements for securing these over-the-air updates, and we should strive for much better security than required by lawmakers. So today we're going to talk about classic and OTA updates and how they work. Then we'll speak shortly about some security considerations when designing these kind of systems. Then we'll talk more in depth about some misconceptions developers have when implementing software update. You can see some examples here, and specifically vulnerabilities that result from these misconceptions. Finally, we conclude with some suggestions for process improvement in order to improve the quality of the implementation and design of the OTA update systems. So let's dive into the intro. So first of all, why do we even need ECU updates? So ECU updates are sometimes needed to solve safety issues. Classic ones are, for example, airbags not working correctly, maybe opening early or late. Maybe we need them for compatibility with installing new components in the system when it's being upgraded. There's cases where there might be usability issues we need to fix, and these can be either a general fix when you come into your dealership yearly or whenever you fix your car, or can be part of a recall. Additionally, we might have to update some function data. A good example is maps, which need to be updated on a regular basis to be relevant. And finally, in new vehicles, we're seeing updates being used to add new features after the car is released. The classic approach for updating ECUs is using a physical connection to the vehicle, usually a diagnostic tester. You can see here the OBD port, which is a port which is usually available under your steering wheel, which the diagnostic tester connects to. The protocols used here are usually UDS, ISO 14229-1. And this actually is a protocol which is based on an older protocol called the Keyword Protocol 2000, which is over 20 years old. So the technology here isn't very new. And in more newer vehicles, we might see diagnostics over IP. But even a diagnostics over IP, when running over Ethernet, is still using UDS for the actual diagnostics work and update. So we're basically seeing that new vehicles which use wired upgrades still use the same technology from already 20 years ago. Additionally, some larger ECUs have larger update packages or more complex updates, which are delivered over USB. Okay, so how does the ECU flashing work in practice when you have a diagnostic tester? So you can see here on the right the flow of messages, but this is only the minimal messages which are required by the UDS standard to be used in order to update the device. But in practice, OEMs implement this very differently, very proprietary, with many more messages. We found many issues in OBD flashing over the last years. Usually the security risk isn't so high because physical access is required in order to exploit these issues. But in the vehicle with over-the-air updates, we'll see later that since these mechanisms are still used, this risk might be higher because it can be exploited remotely. So what are over-the-air updates? These are updates that are delivered from the OEM cloud, in the case of a vehicle, and directly to the vehicle itself. And these have many advantages. You can see some here on the slides, but there's no physical connection that's needed. So how is this delivered? We deliver it over cellular or Wi-Fi. And these delivery methods have their own security issues because they're wireless communications and can be possibly tampered by an external entity. And we'll see how this is relevant for some of the issues we'll discuss today. But clearly, this allows us for lower costs, rapid deployment, and of course, what we've seen, which is very cool in the last couple of years, performing remote recalls without having to bring in all the vehicles to be flashed in the dealerships. So how is ECU flashing implemented when we have over-the-air updates? Usually we have an entity called the over-the-air update manager, which is supposed to centralize this process. What it needs to do, it needs to fetch the updates from the server. These need to match the hardware and software configuration of our specific device. These updates need to be cached locally because we don't know that we're going to have connectivity for the rest of the process, but rather only while we're downloading. Then we need to flash individual ECUs in the correct order. And this is essential. This order has to do with software interdependencies between the different ECUs, but also we might have multiple updates applied at a single update for a specific ECU, and also those are really important to do in the correct order. In our labs, we've bricked multiple pre-production devices due to updating packages in the wrong order. So make sure when you implement this that you have some safeguards in place so this won't happen. Then we have to decide if we're going to harness the existing classic solution, UDS over CAN or diagnostics over IP, or develop a specific OTA interface for flashing individual ECUs. We see that most OEMs are implementing this OTA-specific interface, starting with the ECUs which were traditionally implemented with USB update. And we guess that over time, we'll see this taking over also where UDS is common. The update manager usually resides as a software component, either on the telematics because it needs to download the updates anyway, or on the gateway because the gateway is usually connected to all the devices in the vehicle, or at least most of them, or on the infotainment, which naturally has a lot of storage, which is relevant for updating. And sometimes we see a combination of all three. We might have the combination of a different component running on each of these in order to allow for flashing to happen in the most efficient way. Next, we've dived in a bit to security considerations when designing these systems. So first of all, we have authorization. We need to authorize the entity performing this update. It used to be that the updates were performed at a dealership. Maybe authorization could be handled in a more physical manner. But today, it's an OEM update system in the cloud. We need to be able to authorize it to make sure that it is allowed to update our specific ECU. We see use of custom authorization systems, such as tokens. Sometimes we see use of UDS security access, but that is slowly being phased out because it's not as strong as more modern approaches. And newer systems are using a role-based approach where your role is decreed by the token, for example, you have. So you could be a user, you could be a mechanic, possibly you could be a design engineer, and each one of these roles gets different diagnostics authorizations on the system and can perform different operations. Next, authentication. So we need to authenticate the backend and the vehicle itself. A non-authentic backend can allow an attacker to attack the entire fleet. So if it's possible to fake the backend, this would be very bad. But also a non-authentic ECU or vehicle could extract the updates. Maybe that's going to expose some IP, which we don't want to allow people to see, but also could attack the backend through this interface. Additionally, we need to think about future-proofing because these vehicle lifespans are getting longer. I've seen some outlets that quote over 12 years on the average age of car in the US, and this is getting longer by the year. This means that software update code must itself be updatable, and also the design needs to be a moving target. We can't just decide that the ciphers that are relevant for 2022 are going to be relevant for the next 10, 15 years, because we don't know what will happen in the next 10, 15 years on the cryptography landscape. Next, integrity. So where should the integrity checks happen? This is a really important issue, and we see that many implementations fail on this design decision. So if we only check the integrity on the update master, this can allow manipulation of the files on the device by another process, or allow physical attacker to flash the ECU by connecting directly to it. So we'll see later how this affects some issues we found. But in order to verify the updates, we also need cryptographic keys. And these also need to be secured and provisioned. So potentially we use the same update system in order to update these keys, or we need to have a separate update system, which again brings in its own complexities into the design. In automotive, reliability is the most important feature. Nobody wants to drive a vehicle which is not reliable, and if the software update will not be reliable, it will not be used. And we've heard of some OEMs which have disabled these kind of features because they were not reliable enough. Before starting the flashing phase of an update, we first need to check some preconditions. For an electric vehicle, we need to check if we have enough battery to complete the flashing. We may require the owner to plug in his vehicle before starting the flashing phase. We will not allow an update during driving because this might compromise safety. We will only update the car with user consent. This is due both to regulation in certain countries, and we don't want to upset the customer. The worst thing that would happen is if you woke up in the morning and you found out that your vehicle was updating and you would be late to work that day. And the same goes for commercial vehicles such as trucks and robotaxis, where the vehicle needs to operate for as many hours as possible to return the investment. If an update happens at a time which was not planned for, this could cause direct financial harm. So regulation is also a major part of automotive development. I won't deep dive into this today, but some points that we should take note of. First of all, for a current set of vehicle software, there's a process called homologation, which is performed. This homologation process is compliance testing, which is necessary in order to be allowed to export and sell the vehicle in different markets. Homologation covers topics such as safety and emissions, and newer regulations such as UNECE and for Europe, and GBT regulations for China now address security and require specific attention to software update in some cases in order to be compliant and be able to sell vehicles. So this process of software update and the compliance here can cause some delays in deployment in security updates. And this is something regulators need to handle in order to ensure, on one hand, a safe environment, but also a secure environment in the vehicle. Specifically, the UN R156 regulation, which is part of UNECE regulations in general, requires the OEMs to track software versions on the specific vehicles for compliance. This means as part of the update process, the server needs to be updated with the exact software version, which is a challenge from a design perspective because we need to make sure that if a certain software version fails, we still remain compliant by rolling back the system. In addition, the regulation requires that the vehicle itself be in a safe state after an update. This also requires rollback implementation because if an update fails, it needs to the update needs to fail gracefully, and therefore we either succeed in updating the entire vehicle or we roll back the entire vehicle to the previous compliant software version. Next, we'll talk about some misconceptions in implementation. So let's assume that all what we spoke about is solved. We have a perfect design. We've written a specification and requirements, and now these need to be realized in code, probably by a supplier. And the question is, what can go wrong? And I'll tell you a lot. So we're going to look through this example code, which we'll be using to show the different issues which we found and are relevant for these misconceptions. And this code has been simplified so we can focus on the key issues. Real OTA code is much more complex. The vulnerabilities we'll speak about now have all been found in pre-production units and have been reported and addressed by the OEMs and suppliers. So nothing here is a 0-day, nothing here is exploitable in a vehicle that we've worked on and we know of. But definitely we believe that additional implementations are vulnerable to these kind of issues. So we've changed some details here. This won't be the exact versions of what we found, also to protect our clients from this information. So the first step here in this code is to download the software update file to the local storage. And as mentioned before, we might have good connectivity while downloading, but later on while flashing, we may have no connectivity whatsoever. We then verify the update integrity, presumably using a cryptographic signature. Finally, if the verification is successful, we flash the firmware to a specific ECU, and then we're done. So our first misconception is that the server is always authentic. So we're going to focus on the download step. When we use a web browser, we're used to seeing the padlock, which denotes a safe website with a valid and secure certificate. This is because we're using HTTPS, which requires certificates in order to both verify and later encrypt the communication between us and the server. So the certificate itself is used to verify the identity and authenticity of the web server. And when this is not the case and the web browser understands that something is wrong, we will see a cross sign, a red cross sign on the padlock, and this will prompt us the site isn't safe. And this, as a user, will allow us to abort and not connect to that website. But this is not something we want to support or is even easy to support as part of an OTA update. And therefore, the code has to handle this without any user intervention. So on the device we examined for this specific issue, the certificate is verified using the OpenSSL library. Any verification failures are reported using the verify callback. And this has to be pre-registered as part of the verification process. So the version that we have here on the slides, it always ignores the error. Okay, it returns 1 regardless of if an error occurred or not. The actual code had some cases which were handled, but most of them were not. This means an attacker could supply an invalid certificate, and the authentication would complete successfully, which means that an attacker can now make you download if you're trying to download the software update, the attacker could now make you download it from them, even though the certificate wasn't valid. So this would still require a man-in-the-middle attack in order to communicate with the vehicle. But as we mentioned earlier, OTA updates can be delivered in some systems over Wi-Fi. In many cases, this makes the man-in-the-middle attack trivial because the attacker can use their own router with some freely available software to intercept both DNS and HTTPS communication and serve the invalid certificate. Therefore, extra attention is required when implementing Wi-Fi-based OTA updates to secure this interface in a good manner. It's also possible, potentially, to perform this kind of attack on a cellular connection, but this would require more advanced equipment and know-how, and of course, it would violate multiple laws in most countries. Additional cases that fall under this misconception are updates downloaded over HTTP. We've seen some specific updates downloaded over HTTPS without verifying the host name and the certificate. In this case, this means that you can deliver a valid certificate, which is signed by a root authority, but it doesn't have to be the certificate for the specific URL, which means any certificate bought from that based on the signature from that root authority is good enough in order to allow an update. And of course, we've also seen updates coming from an FTP server, which was not secure. Now, one might ask if this is enough to exploit the device, because there might be hashes or other protections along the way. But usually this is enough in many systems to allow a downgrade attack. This means that we will update the system with a previously released update. And this can be done in order to open a vulnerability which was closed in the current software, or possibly revert the software version to allow a feature which has now been removed in a newer version to be used now by rolling back to the version where it was still available. The next misconception is that using a signature is enough. So we return to our code, and now we'll focus on the verification stage. The device we examined had multiple implementations of over-the-air update for different partitions and components. So one of them had code which is very similar to this example. And the first thing that happens here is we can see that the verified software update package receives the path of the downloaded update. The function has two buffers for the received hash, which is coming from the update file, and also it has a buffer for the calculated hash, which the function will calculate. The function then copies the received hash from the file itself, and then proceeds to calculate the hash on the remainder of the data in the file. It then compares both hashes and returns true if they are equal. Okay? In essence, an attacker can provide an update here with the correct hash, and it would be flashed. This check is not really verifying the software package. It's rather looking to see if the software update was corrupted in transit. And this is why we need an actual cryptographic signature. And this would not be enough in order to protect us from an invalid software update, an unauthentic one. So a signature check should never be possible to skip in production, and this is also one of the things we've seen in some devices. There really shouldn't be alternative signature types in production. We've seen a device where a CRC32 checksum was allowed to be used instead of an RSA signature. Some other notable research, which I think was mentioned earlier today, was published by Green Luigi 1 earlier this year. They found that the 2021 Hyundai Ioniq Special Edition Limited Infotainment used default encryption and signing keys. They were able to flash their own software onto the device. This set of series of articles is really worth a read, and you can find a link to it at the end of my slides. Local storage is secure, or maybe not. Insecure storage is a really big issue with these software updates because, as we mentioned earlier, most OTA updates need to cache the files on local storage. This means that the local storage is now an additional attack surface on the over-the-air update. So what is actually happening here? So we've seen that the actual update file and update data is not passed around in a buffer, but rather is written to a file and then read from the file. But it is read two times, one as part of verification and one as part of the flashing. This kind of issue is called a time of check, time of use, or TOC2, and it's very common in OTA and in classic implementations of updates. Basically, what's happening here is that the update is read twice. Between these two actions, the file can be manipulated, but we will not know this because the verification has already occurred, and we can now manipulate the file. Then the flashing occurs and reads the manipulated file from the drive. This can be done by another service that has already been compromised by the attacker, or potentially by using physical access to modify the flash, which is of course a bit harder, but still possible. An update should be read a single time into memory once to be verified, and from the moment it is verified, it should not return to the disk, but rather be flashed immediately. Okay. Then it's important to note that even if the update is verified again on the ECU being flashed, it's still possible to exploit this issue as part of a downgrade attack, which we described earlier. Additional cases we've seen. Over-there update files that are stored in encrypted storage, over-there update files that are accessible by other processes. And as you probably figured out, we rarely see an automotive update system with no issues. So this is, again, very common to see issues with the secure storage. The reason is that there is usually a responsibility split between the over-the-air update development teams, and the platform security teams, which deal with the secured storage. And many times the requirements are just not detailed enough. Another good example is an issue found as part of a larger research by Tencent Keen Lab researchers on the Tesla Model S, which they published in 2017. They found that the gateway ECU, some updated related files are stored on an SD card, and this interface allowed them to find the vulnerability, which they exploited to reprogram the device with their own software packages. A link to this research is also at the end of the slides. We now come upon the end of this presentation, and we're going to talk shortly about suggestions for process improvement. These are some things that we've noticed and have helped our clients provide better software update systems. So first of all, this was also mentioned in the keynote earlier today, don't reinvent the vehicle. OTA design should be based on experience from other industries, such as the cell phone industry and IoT industry. You have to make sure to write detailed requirements. Some examples for these are what should happen in different cases of failure. This should be very clear. What are the acceptable cryptographic ciphers, and what should happen if a non-supported cipher is used in a signature? What behavior isn't allowed under any circumstances, such as mentioned earlier, skipping the signature check, which should never happen on a production device. Additionally, you should try and avoid mechanism duplication. You should try to consolidate the code for classic flashing with over-the-air flashing. You really don't want to have two separate sets of vulnerabilities in the same device. It's hard enough managing one stack. And you should share your design across ECUs. This will allow you to invest more time into ensuring the quality and security of a single implementation. And as the OEM, you might want to provide this as standard software to your suppliers. And this way also, you invest more time in a single design, which is shared across multiple ECUs. Make no assumptions. I think this should be clear from the examples I brought earlier. You should follow best practices, defensive programming and multi-layered security. Ensure that if one security layer fails, the next layer can block the attack. Additionally, testing suites, static analysis, and fuzzing are very good at providing coverage of cases which are hard or tedious to check manually. Share implementation across generations and variants. This is something that doesn't normally happen in automotive due to the responsibility shift, but really this should happen more frequently, and we're hoping to see this in the future. This simplifies all tasks and allows for development of a mature implementation. And this really works well with what we suggested earlier, that an OEM should consider providing this as standard software to their suppliers. Performing code reviews and penetration tests is, of course, still important. As part of code review and penetration tests at CYMOTIVE, we focus not only on memory corruption bugs, which may be better addressed by automated systems, but rather on the logic bugs, which we showed earlier, which are harder to find with an automated system. We also perform end-to-end penetration tests, which involve in-vehicle, cloud, and mobile components, and allow deeper understanding of the entire system. This approach has allowed us to find bugs that wouldn't be exposed by a penetration test on an individual part of the system. And this also would cover additional cases which we didn't touch today on the backend side of software update. A couple of general notes are that we believe that standardization of software updates, maybe through the AutoSAR consortium, is the way forward. This feature of software update isn't necessarily a differentiating feature for OEMs, and as such, a standard solution is good for most players in the industry. People are more likely to think, are there over-the-air updates or not? They don't necessarily care about the process happening behind the scenes. An open source reference design and open source reference implementations can help architects and developers learn more about how to secure software update. The Optane project by the Linux Foundation provides an open software update framework designed with emphasis on security. An Optane in-vehicle implementation is provided by automotive-grade Linux in an open source project which provides customizable Linux distributions for vehicles. These are great resources for learning more about practical software update implementations. And of course, share your experience with the community so we can work together on improving OTA update systems for everyone. I'd like to thank my colleagues because this presentation wouldn't be possible without their help, and especially to my friend Gal, who reviewed these slides. And with that, do we have any questions?
So thank you, Benny. Yeah, so we have time left for only one question. You can see it on the screen, right?
So if I've encrypted my firmware and authenticated using RSA, and assuming that there was always a backup firmware version, do I still need a secure backend? Yes, so we mentioned before that a downgrade attack would be possible in this kind of situation if there's no anti-rollback mechanism. And this means that if the backend isn't secured, you can just use the same update file from a previous version in order to downgrade the device. So yes, we still need a secure backend.
There is some question on the chat, not in the question answer tab, so I can't share it. But someone wrote standardizing the OTA in the automotive domain is good idea. AutoSAR is already in this direction. Also, Automotive OS considers OTA and platform features specific standardization. Specific to OEMs. What is your view about standardization, the OTA design in automotive industry?
So I mentioned that shortly at the end of the slides, but yes, definitely automotive OTA should be standardized. It's not a good idea, this fragmentation we have now. We're seeing different issues, but many issues across suppliers. And we believe that similar to what AutoSAR has done to the industry, decouple the function development from the base software, the same should go for OTA. There can always be some extensions for specific OEMs, but we believe that standardization is the way to go forward.
Thank you, Benny. And if anyone has any more questions of Benny, of course, go to the networking area and you can just go direct to him. Thank you so much for the presentation.
Thank you very much for having me.
Bye. Have a good day.